So ss4 is about ions, and that's why I'm dressed like Tigger, because Tigger is always positive, because he is a cat, and just because somebody gave me the hat, so I could. This study set has a purpose of at least getting you familiar with ions, and it makes my life and your life, you just don't know it, when you go to do the lab, that much easier. Because if I don't have the study set and quiz today, nobody does anything, and then the lab, everybody's just lost. So this way, at least by the time we get through this, we're going to do some practice after that. It should make the lab, especially in this environment where I don't get to be face-to-face with you all, run smoother. All right, it also brings in question one was just to show you everything we've done so far. We just keep building on it. The problem with this question is they didn't do the noble gas configuration. So the valence electrons, you have to kind of find the noble gas. The valence electrons are what is after the noble gas. So this one would be 8 valence electrons. When we get to number 2, I'll show you an even easier way. So this one, it would be the 3s. So the 3 S's and 3 P's, so 3 valence electrons. In this one, just 1 valence electron. And in D, there are 2 answers I would accept right now, and then we're going to segue to it in the next question to our preferred answer. So you could say 17, because after the noble gas core, which is argon here, we would have 17 electrons. But the 3 Ds, once they're full, they don't react. They do allow interesting things to happen. So really our answer is 7. The valence electrons, an alternative way to talk about it, and it's probably why I talk about it this way, because I'm a biochemist, is we look at the S's and the P's in the outermost shell, because they're going to be the ones that react. Now, when and as a biochemist, I pretty much only work with non-metals, mostly. The ones in the middle, in the D block, there we do care about the D electrons, but once they fill up the D block, those D electrons are stable. So the next question, and we're all going to renumber our periodic tables. So as I mentioned in the video, and I mentioned again in videos, and my other class is a week ahead of you, because they actually have more hours with me, because it's a 5-credit class, that we run into a bigger conundrum than we do today if you don't renumber it. And so last night we all renumbered to my A group numbers. So the first and the second column, it's not a big deal. They'd be 1A and 2A. The other thing that you're going to hear me recommend throughout today is, if you did not, as I said in the video, at the top of your columns, put your charges for those columns. If the 1A's are +1, the 2A's are always +2. That is something that will be very helpful with the lab. All right, we're going to ignore the middle for now, and then we move to the other side of the periodic table. And so the S and P blocks are considered the main group. The transition elements are in the B's, and they just have an alternative numbering way. We're not going to worry about that. It's the A's that matter. So what was 13, 14, 15, 16, 17, 18? If you have not already renumbered it with the A's above it, 3A, 4A, 5A, 6A, 7A, and 8A, please do. Because not just this week and into next week, but in 2 weeks when we get into Lewis structures, it's a total game changer. Otherwise, it's not gonna, it's gonna make your life more challenging. The other thing, while I have this up, is it goes with question number 3 and 4, that they gain or lose electrons. So the nonmetals are always gaining electrons to become like a noble gas. So the halogens, fluorine, chlorine, bromine, iodine, they're going to gain 1 electron. Oxygen, so they're always a -1. So labeling above that a -1. Above oxygen's family, oxygen, sulfur, selenium, tellurium, they're always going to be -2, because they're at 6. They need 2 electrons to get to the 8. So it's not so much you're counting boxes, it's how many would they need to get to the 8. It's a difference there. And so nitrogen's family would be -3. Carbon, I didn't put a charge above them because in nature, that family, carbon and silicon, do not make charges. We as humans have made them into ions. Carbon and silicon will be anions, but germanium, tin, and lead are cations. And so, anybody know why? So you should all know why, which is the staircase. And so if you can't see the staircase becomes really important when we're working with ions and as we build. This was the difference between our metals and our nonmetals. So above the staircase to the right are the nonmetals and below are the metals. Now on your midterm, the first midterm, we were refining, there are the metalloids. So like boron, silicon, germanium, and arsenic, the ones that are touching the staircase. For our purposes, because we're just in the introductory class, if you're above that staircase, you are going to form a negative ion. And if you're below it, you're going to form a positive. Boron also does not form an ion. So that's why I labeled this group as +3, but we're going to refine that. So like aluminum is going to be a +3. The ones that do touch the line, it is actually more involved than that, but it is beyond the level of this class, so we're not going to worry about it. And that is something that will help you a lot with the lab and with what we're doing. And as you do this, it will start to make sense that you won't have to necessarily always have that there. Something students in my other class, and don't worry about this, I'll talk about that after the homework. They actually made multiple copies of periodic tables so that they could just keep writing different things. And some of them actually laminated one because they said that way they could erase what they did with a towel. So that's something that can be helpful. All right, so the group, magnesium's the 2 or the 2A, and it's going to have 2 valence electrons. So their A group number is their valence electrons. Potassium is a 1 or a 1A, and so it has 1 valence. So I just write BAL for valence. Phosphorus, if we've now renumbered it to 5A, phosphorus is there below nitrogen, it is 5 valence electrons. Now, if you wrote 15, you can just make a note next to it because those D electrons are not going to react. And so it's, yeah, and if you take another chemistry, go with how your teacher wants it to be. I'm doing it this way because it will make this lab and other things that we're doing much smoother for the rest of the term. All right, so 5 is, I'm sorry, bromine is in the halogens. So it was group 17. We're going with the old nomenclature way, which is 7A, which gives it 7 valence. All right. So the periodic table, Linus Pauling, won 2 Nobel prizes. He always used the A group numbers too. So, and he's one of my heroes. And he's from Portland. All right. The chemical property of noble gases is they're non-reactive. That's all I wanted there. And that's how we know that they're stable. They don't react. They did not exist in Mendeleev's original periodic table and all the alchemical tables. Nobody knew about them until about 120 years ago. And it was looking at light spectrums that they realized there were other things in air, other gases. And again, the first one was argon. They called it lazy because it didn't react. So that's actually what the name argon means. All right, the octet rule is that all the other elements gain or lose, or they share electrons. So we haven't talked much about sharing, but we will in 2 weeks. We'll talk a little bit today to become like a noble gas. And with that, it was called the octet rule. I don't remember who coined it, because these were called the 8 A's because they had 2 S's and 6 P's, and that gives them a very stable configuration. And so the octet is 8 valence electrons if you use the A group numbers. All right, the symbol, we always write, if there's 2 letters, the first one is capital, the second one is lowercase. I write my chlorine in cursive, so you don't think that's an I. Do not write it as a capital L. That is something that would be marked wrong. Charges are shown after as a superscript. When it's a 1 charge, we do tend to just show the negative, but if you write it as a -1, that's perfectly fine. I have no problem with that. All right, sulfur, when it gains 2, this is another thing I mentioned in the video. It technically is 2 negative, but a lot of students, it makes more sense if they write it as -2, because when you learn positive and negative numbers back in somewhere in life, you always put the charge before it. So you can write it as 2 negative or -2. Potassium would be a plus or a +1, and beryllium would be a +2 or a 2 plus. So again, that doesn't matter to me if you show the charge before or after the number. All right, number of protons. So they all keep the protons that they were on the periodic table. So sulfur is 16. What changes is the electrons. That was something I kept commenting is back when we like filled in the charts and stuff. So sulfur is 18. Fluorine is number 9, so 9 protons, and now it's 18 electrons. Potassium's 19 protons, and it loses, so it becomes 18 electrons. And hydrogen is special. It is 1 proton, and then it loses the electron, so it is 0 electrons. Hydrogen ion is the same as a proton. And if you remember when we talked about protons, they are tucked deep, deep, deep inside of the atom. 99.999999999. They keep adding more and more nines is where the electrons are. It's emptiness. It's where the vibrations, the intentions happen. And so what happens when this becomes loses its electron, it loses its whole house. It like that huge castle and protection and moat and everything that was around it, it's gone. This is extremely reactive. And so these get a special category, and these are going to be the acids, which I'll talk about after we go through the study set, but you might want to make an indication there. And this is why they get a special category, is because they are a proton, and so they're going to burn, they're going to corrode. This would be if we were in lab, I always have to put a warning when we work with acids. So like if you have a cut on your hand and you happen to get some vinegar on it, you're going to feel the sting because it's burning, because it's a proton and it's looking for a home. And so that's what the burn is chemical reactions are happening. All right, the charge, lithium is a +1, phosphorus is a -3, sulfur would be a -2, and aluminum is a +3. Now, if you're still having trouble with that, please, I actually would tell all of you to make the time for office hours over the next several days working with this lab, because this lab is a whole language that we're going to be doing. What this study set is just the idea of ions. And once you can do that, then we can add the next layer of all the pieces. But again, these guys have 1 valence, these have 2 valence, so they lose to become like a noble gas. On this side of the staircase, they're going to gain. And we'll worry about the ones in the middle after we get done with the study set. All right, on this one, rubidium, sorry. So it is rubidium, but I had a student in my other class called it rub-a-dub-dub, and so you'll sometimes hear me say that. I mentioned the correct name because I had a student one year, and I was called FR frankincense, and it is the Christmas season coming up. And so she was in the Christmas pageant, and she was so excited at church to tell everybody in her church congregation that frankincense is an element in the periodic table, and it's an alkali metal, and she was so excited to tell me how much she'd learned. And I stood there with my jaw dropped going, oh, that's been a joke I made. So this is not rub-a-dub-dub, it is rubidium, but it loses an electron. Now, I am going to caution you, having looked at this study set for a decade, if you write this as -1 because you're just trying to do a shorthand, you're going to confuse yourself when you go back in a month to look at the study set, because rubidium is not a -1. It's losing an electron. And so when it's losing a negative, it actually becomes positive. All right, iodine is going to gain 1 because it is a non-metal. Oxygen's going to gain 2, so 1 electron, gain 2 electrons, and sodium's going to lose 1 electron. So do write the word, and same with, let's say on the next midterm, if I ask that question, you do not want to say minus. If I asked for the charge, you would, but if I'm asking losing or gaining, you would want to actually write that word out. All right, I didn't mention this, but iso means the same. You could probably have figured it out. And then you see the word electron. So it's going to end up as the same electrons. And the only thing we want to be the same as is the noble gas because they're stable. So you may have, without knowing that or deciphering the word, said, well, fluorine ends up like neon. Aluminum ends up like neon. Titanium actually ends up like argon in this form as a +4. Now, titanium can be other charges, and in those other charges, it would not end up like argon. So the ones in the middle do not always become like a noble gas. Selenium is going to come out like krypton. So selenium's here, number 34, and with a -2, it comes out like Kr. All right, and then question number 10 was just like what we did to remind you, this all comes from, we're building, we just keep building on the information. So that also goes with your first midterm, it was graded and you should be able to view it, no problem if you go into your grade book. And a question that often comes up from students is, do we need to know any of that information for the next exam? Well, in some ways, no, but it is these electron orbitals that explain the valence electrons, and then why this is going to gain 2 because it wants to have the S's and P's filled. So it had 2 unpaired electrons, so it gains 2 to pair them up. The other thing is all that math stuff. That's what we get back to next week. Next week's one of those math weeks, so make sure you bring your calculator. So we keep building on the information from the previous info. Was there any questions on the first page? All right, so question number 11 is then the key. The first side was getting the idea of charges, and on this side we put it together. So what has to happen when we put it together? We do not show the charge, we show the ratio. So this has to be the lowest whole number ratio, and so that it is to make it neutral overall. So if lithium's a +1, it's losing 1 electron. Each oxygen wants 2 electrons, so we need 2 lithiums. Here, if they have the same charge, equal but opposite, you just need 1 of each. So aluminum and nitride. We always show the cation first. Same potassium chloride, just 1 of each. And then here, the magnesium's giving up 2. And so something you want to be very cautious about. Don't say, well, I need 1 more iodine. It's always how many iodines you need. That you're going to need 2 iodines to balance the magnesium. And that is actually the first page of the lab. By the time you get through that, and we're going to do practice, this should become pretty straightforward that you can do it. All right. Here, you're going to write your ions first. And on the lab, you're going to write your ions. And I will tell you this, because again, my other class is a week ahead of you. That's the most missed part of the lab. Because Google doesn't tell you what the ions are. And so I can tell who doesn't get it because they end up being really sloppy with their ions. They get the names because they copied from somewhere, but they're not understanding what the ions are. And so take the time. You got to spend the time on this lab because this lab is a building block. It's a huge building block. It's like the math lab. And so you want to make sure you spend the time so you're ready to move on, because we move on next week and add much more. So you're given a grace period with this lab. It's due Tuesday, but I would have it done before that so that you're, if you have questions. So I'm gonna have more office hours as we finish this week out, especially today. All right, so calcium and oxygen. So predicting the charges, label your periodic table. So calcium is a +2, oxygen's a -2. And again, you can say 2 plus, 2 negative, that doesn't matter. If they are the same charge, you just put one of each together. Right. Aluminum is a +3. So again, aluminum is below the staircase, so +3. Iodine's a -1. You can just put a negative. Again, you can put a -1 because for a lot of students, this ratio makes more sense. So for every 1 aluminum, I need 3 iodides, so that the charge comes out as a +3 and a -3, so that they balance. All right, barium is a +2 and nitride is a -3. Now, a question Tim had asked me actually before class was about the endings of the ides. That ending ide actually tells us that we have made them into ions and they're now in a stable form. So oxygen is highly reactive. It's one of the most reactive elements. It's what drives our life. But as oxide, it has already reacted and now it's in a stable form. Same with iodine, all the halogens, fluorine, chlorine, bromine, iodine are extremely reactive. And as soon as they find somebody to take an electron from, they do and become the iodide, bromide, chloride, fluoride. All right, there's one right answer here. And again, this is what the purpose of the lab is. And what most of you end up seeing is the 3 and the 2s always switch places. The reason they always switch places is the lowest whole number that they have in common is 6. So this is what I was trying to show in the video, and it usually takes a couple times seeing it, and that's why we're doing practice today, where you have the study set, is the 6s, to get 6, you need 3 bariums. And to get to -6, you need 2 nitrogens. And that's why they're always going to switch. So some people, the 6s make more sense, and some people, they just swap. All right, number 13, to be ionic, we're looking for metal, nonmetal. So A, B, and D. C is not, it is 2 nonmetals. And so it would make a covalent bond. And we'll talk about them more after we finish the study set. And we talk about them a lot more in 2 weeks, and actually next week also. The other thing I want to mention with this question, and you'll see, and I know I mentioned it in one of the videos, everything that we're doing is binary, which means we just have 2 parts. So we have a metal and a nonmetal, or here we just have 2 nonmetals. In the real world, so like in geology, these have multiple metals and multiple nonmetals combining, but the ratio ends up being neutral overall. Or in the wonderful world of biochemistry, covalent molecules have multiple different types of atoms, different elements, but we're going to always just combine 2 pieces. All right, the chart again. Iron is still number 26. We subtract to get the neutrons, so that rule is the same, and we actually don't do anything more with neutrons the rest of the term. So that is one of the pieces. That's not actually true, because next week we're going to do calculations. We just don't count the neutrons. They're there, they determine the mass. The mass is the protons and neutrons. The electrons now, we lost 3 because the charge is a +3 or a 3+. So that means we lost 3 electrons. All right, on the next one, we also lost 3 electrons. So it's a +3. So it's our difference between here and here. Number 28 is nickel. To get the mass number, we just add these together. So we're at 59 again, and we'd show our +3 or 3+. as a superscript after. The mass numbers we're not going to show anymore in this class, but the charges we will. All right, number 77 is IR, which is not iron. Iron is Fe. IR is iridium. It's the second densest element. Anybody know what the densest element is on the periodic table? It's where I ponder if anybody's actually there, because you're all black boxes. So some of you have pretty pictures that I can look at. So I'm going to pretend like Michael's Raven is going to talk to me. And so iridium's really important because osmium's the densest. Iridium's right next to it, almost as dense. It's only found anywhere asteroids have collided with the Earth. So one thought is there is no natural iridium on this planet. It only came from outer space. But really, is there anything natural? Everything came from the great beyond. All right, so it'd be +2, and we add it together, 197. All right, and then the last one, if it's -1, it gains an electron. So it must be number 9, which is F, has a negative charge, and these two would give us our mass number. You can say bye-bye to the mass number. We won't see that again. I don't think it even shows up on your quiz today. All right. The period 3, so period means the row. So we're going somewhere from sodium over to argon. So if it has a -2, that would be sulfur or sulfide. A +2 would be magnesium. A -3 would be phosphorus. And then a +3 would be our, aluminum. And again, you can show it as a +3 or a 3+. All right, question 16 is another one that is really important. And this question we're going to see again. So hopefully those of you, I do look at your study sets, and some people write, have no idea. Hopefully you have a red pen with you and that you're filling in. So again, as I go through the study set, I recommend you fix it as you go along. So that this is for you, for when you study for your midterm. So ionic means we're losing and gaining electrons. So we have a positive and a negative. And the big key here is this is an electrostatic attraction. So electrostatic just means, it's a fancy word humans use to say positives and negatives attract. So it's an attraction. And so because of that, they are a ratio. It's that Lewis whole number ratio I wrote up above. So they're just an attraction. It's like holding hands. They will easily come apart. Just put them in water and they come apart. They're more attracted to the water. Covalent, on the other hand, is sharing electrons. This is the only true type of bond. Ionic is not actually a bond. And so this is 2 or more nonmetals. So nonmetals or nonmetals only, they share electrons. They both want to gain, so they have to share and to get to the octet. And so that sharing is holding them together, and that makes them a discrete unit. These are not a ratio. CO2 is a carbon with 2 oxygens, whereas MgCl2 is just a ratio of 1 magnesium to 2 chlorines. These are called molecules. Ionic compounds are not molecules. Yeah, and back to the ionic versus covalent. The other thing, which you all know, is metals and nonmetals. So the metals are losing and the nonmetals are gaining, which is what the next question is. So A is false, because they do not form cations. Nonmetals form the anions or anions. So I'm Tigger today. I'd be a cation because Tigger's a cat and he's always positive. So Iori, he was always like glum and negative, and he probably ate onions all day or something. All right, nonmetals, gain electrons, so another EORI false. All right, positive are cations, that is true. So C is true. And D, transition elements, this is false. Transition elements cannot form, they do not form negative. They are metals. They do form positive charged ions. And then the last one I'm pretty sure is true. Yeah. So chloride means it gained electrons. So I call this the Thanksgiving rule. When you eat more, it's Halloween. If you're going to eat a lot of candy, you're going to become ill inside, but you're also going to gain weight. If you lose electrons, they actually shrink quite a bit. And that is because they actually lose a whole shell. So the cations, so like when, let's say, calcium loses its 2 electrons, it actually loses a whole 4th shell. So it loses a whole layer to drop back to become like argon. All right, questions on the study set?
I have like a question in terminology. So like an ion, that just means it gains or loses electrons. Is there only one ion for each element? Like, is there only one possible ion for oxygen?
So your oxygen, there is no. The answer is no. There is one stable, there is a stablest ion. So oxide is -2. You picked a can of worms to ask me about oxygen. So chlorine is -1. That's the only ion for chlorine. Oxygen does some weird stuff. So there's peroxide, there's superoxide, there's hydroxide. Our body has a whole set of enzymes. This is why people eat fruits and vegetables, to deal with oxygen's problems. Oxygen is a very troubled child. It's so desperate to gain 2 electrons. It does anything it can. We are going to deal with oxide. So now the other thing with your question, the 1As and 2As, yeah, they're always +1. That's what I'm going to talk about in a moment. The middle, these guys form different ions. And so that's what we're going to talk about now. So the term ion means charged particle. It actually means wanderer. But they are charged particles. They can either be positive or negative. Anybody else? Yeah, and what we're going to move into, I will cover that a little bit better. Go ahead. Somebody said yes.
I have a question on number 14 on nickel. I don't understand how you got the charge of +3 on that. Bitch!
You're looking at the protons and electrons. And so since I gave you those two, the protons tell you it's nickel. I know you get that, but here we lost 3 electrons. So the difference between 28 and 25 is 3. So it lost 3. So that's where the +3 charge came from. So when you lose, you become positive because you're losing negatives. Does that help, Stephanie? Maybe you can ponder that one.
Yes, it does. Thank you.
The problem with this question, number 14, that none of you are recognizing, these iron, nickel, and iridium, they're back to the previous question somebody asked, and Tim had asked me during office hours. When we're in the middle, they form different charges. And so nickel actually can be a 2 or a 3, but in that specific example, it is a 3. All right, anybody else? I'm going to stop recording, and then I'm going to move to the other part to record.